Hi, I'm Nikki Reynolds, an engineer at Tektronix. In this XYZ series video, we'll be learning how to look at and analyze electronic signals. To do this, we'll be using a Tektronix TBS 2102 oscilloscope, as well as an AFG. Now, these are great Tektronix instruments, but the techniques you'll learn in this video can help you use any digital scope. The basic reason for using an oscilloscope is to look at signals. So in this first video, I'll show you how to set up probes and how to adjust vertical and horizontal controls to fit your signal neatly into the display. After this video, watch the next video on basic triggering, and in less than 20 minutes, you'll have the basics. Sometimes you can get away with cheating thanks to Autoset. It uses the processing power in the scope to try and fit signals in the display. But you're not off the hook. Every engineer needs to know how to set up probes and how to make manual oscilloscope adjustments. Probes are often underappreciated. They're responsible for actually capturing the signal and actually impact all of what you see on the signal downstream. The most common probes divide or attenuate the input signal by 10. These are called 10x probes. They can measure relatively high frequency signals and have good voltage range. You need to adjust or compensate these probes to match the scope input. To compensate these probes, connect its inputs to the compensation output. I'll use Autoset to get the compensation signal on the screen. Use a small tweaker, which is usually included with the probe, to turn the compensation adjustment on the probe until the signal looks like a square. When it does, you're all done. Now I'm going to let the scope know that we're working with a 10x probe. The scope will adjust all its scale factors and measurements accordingly, so I don't have to do the math in my head. There are other settings for probes with higher or lower attenuations. Let's say you're not using a probe, but you're using a cable to deliver the signal to the scope's input. The attenuation should be set to 1x, which you can do here or here at the bottom. Using this attenuation, make sure that the scope doesn't apply any scaling to the signal. Most of the time, you'll be measuring voltage waveforms, but in some cases, you may want to measure current. In these situations, you can set the probe type to current, and the scope will display amps instead of volts. For the rest of the video, I'm going to be using a function generator and a couple of cables. So I'm going to leave the attenuation at 1, but I'm going to switch the probe type back to voltage. Now that the probes are taken care of, I'll move on to the vertical controls. We'll just keep it to one waveform for now so you can see this a bit more clearly. The vertical controls configure the y-axis of the display, which is usually, but not always, represented in volts. The vertical scale appears to make waveforms taller or shorter, but in actuality, it determines how many volts are in each vertical division of the screen. The vertical position control moves the waveform up and down. Pushing the knob brings the baseline back to center. The channel menu buttons turn the channel on and off, and also open up the channel menu. Coupling is a useful vertical setting. It defines the way the signal is connected to the oscilloscope input. DC, or direct coupling, passes both AC and DC components of the signal, so you can see any DC offset if the signal has it. AC coupling blocks any DC offset in the signal and passes only the AC component. This mode is really useful when you want to look at the small fluctuations riding on a DC offset, like ripple on a DC power supply. Ground coupling disconnects the channel from the input signal and connects it to the 0-volt reference to show the measurement ground level. For the rest of this video, we'll be going back to DC. I've covered the probe and the vertical settings. That leaves the horizontal settings. The horizontal controls determine the X or time axis on the display. The most important controls are the horizontal scale and horizontal position. Kind of how the vertical scale could make it look like we could made the waveform taller or shorter. The horizontal scale makes it look as if we're stretching the signal wider or more narrow. When in reality, this changes the time in each horizontal division of the display. This lets you look at signals with different frequencies or focus your attention on signal details. For example, a square wave might look like it's making a perfect instantaneous transition. However, if you speed up the horizontal scale, you'll see that the transition takes a measurable amount of time. On most digital oscilloscopes, as you change the time scale, the sampling rate also changes to make the best use of memory, as you can see here. The horizontal position shifts the waveform left and right so that you can see different parts of the signal. Thanks for watching the XYZ oscilloscope video on how to set up probes, horizontal and vertical adjustments. Be sure to check out the next video on how to use triggering to get that perfect signal capture. Thanks.